Okay, everybody, so topic of today's video, functions that are represented by a power series. Now, this will not be my first video about power series. There have been others that come before this one. They set things up for this one. I'm afraid that with this topic of power series, there's a lot of details, a lot of fine print. I would say even by Calculus 2 standards, it's a fairly complicated topic. All right, so you don't want to start with this video if you happen to be here and you've never even heard of a power series. But nonetheless, I thought we'd start with something simple just to get our minds thinking in the right direction. All right, so I ask you this question: why is this true? Why is it that the function 1 over 1 minus x is equal to this series, which happens to be a power series, 1 plus x squared plus x to the third, and so on? Why is that a true statement as long as x is in between -1 and 1? Well, the answer to that is fairly simple, all right? This is a geometric series over here. And that's the first kind of series we learned about. It's a geometric series. We can recognize that any term in the series times x gives you the next term. So the common ratio is equal to x, and it will converge to the first term, which is 1 over 1 minus r. Okay, so this series converges to 1 over 1 minus x. That's this function. And why do I call one a series and the other a function? Well, because this is a series and this is a formula, all right? And these two things are equal for any values of x between -1 and 1. Oh, why is that statement only true if x is between -1 and 1? Well, because a geometric series will converge if r is between -1 and 1. And if I'm saying that r is equal to x in the case of this statement, then this statement is true if x is between -1 and 1. All right, now I wanted to lose the abstraction of this for a second. And what do I mean by abstraction? Well, so this is a concrete statement. There is nothing left to the imagination right there. It's 2 times the number 4 plus 5 is equal to 2 times 4 plus 2 times 5. That's just true. You can do the math if you want. What's this? 2 times 9? That's 18. What's 8 plus 10? That's 18 also. But that's different than saying a times b plus c is equal to a times b plus a times c. I could say that, but if people can understand this just fine, some of them get totally lost if I write it that way, even though this is saying that other thing is true. So, all right, here's what I mean. I thought that, what if we put a number in for x, and maybe you get a better feel for what I'm saying is happening here, okay? So I thought that we would do some calculations with this statement up here, okay? So I've chosen various values of x. All of them are within the interval here, okay? I thought I would put those numbers into the function, 1 over 1 minus x. Oh, so that's this. I thought I would put them into a few forms of the truncated power series. Like if I say 1 plus x squared plus x third plus x to the fourth, that is part of this. It's not all of it, because this series goes on in that pattern forever. Well, I can't write down forever. I only live so long, so I can't write the whole thing down. But I can write it down to x to the 4th power. I can write it to x to the 5th power. I might even say beyond that, even though just for the sake of trying this out and doing some math, the more these terms I write down, the more this is going to be like that. They won't be equal anymore. This equals is only true if this is infinite, if that's an infinite series. If I truncate it at a certain point, it'll only be approximate. Let's try it. So if x is 0.7, the function 0.588. This series up to x to the fourth, 0.687. But if I take it up to x to the fifth, I get a little bit closer. It's a little bit better. Okay? So yeah, the more terms of that I use, the better it is an approximation to this. What about negative 0.3? The function gives me 0.769. This series, 0.7 or so, 0.77. This 0.76. So that's getting it right almost to 3 decimal places. And I continue and I continue, all right? So that's the idea. That yes, the series will be equal to the function if the series is infinite and you plug in an x. We mortals have to truncate the series, and in that case the series will be approximate to the function. All right, the more terms of the series you have, the better the approximation is going to be, and actually the closer to the middle of that interval right here, the better the approximation is going to be also. Okay, so I thought we'd play around with some numbers, hopefully to get a better feel for it, because all these statements are very abstract, all right? They're like this, a times b plus c. It might help you to occasionally think of them like that, 2 times 4 plus 5, all right? Okay, so that's where I want to begin. Now let's do an example, all right? Find a geometric power series for this function. Can you give me a series that is equivalent to that function? All right, that's the idea, right? That's what that other problem was about. Okay, that a series can behave just like a function when you put in different x's within some specified range. Okay, so when I look at this one, then I think, well, okay, I want the series and I have the function. Can this be like a1 over 1 minus r? That's what geometric series converge to. Okay, so I might think about it like that. And I'd see, well, this has got to be 1 minus r. And that's a 6. So the first term, it can be whatever the first term happens to be. And then it's got to be 1 minus r. So the 6 is what is bothering me about that. So what I'll do is I'll take this 1 over 6 plus x, and it being a fraction, I can multiply both the top and the bottom by 1 over 6. That's effectively multiplying it by a 1, so I can do that. So I'll get 1 over 6, and then 1 plus x over 6. Okay? And now I'm almost there. I'm almost seeing that the way that I want to see it. I'll look at this function like 1 over 6, 1 minus, because the formula has a minus in it, 1 minus negative x over 6. Okay, so this is the sum of a geometric series that has a first term of 1 over 6 and r a common ratio of x over 6. Okay, so there's our statement. All right, so I could say something like this. Then I could say 1 over 6 plus x is equal to 1 over 6. That's the first term. Minus x over 6 squared, right? R is negative x over 6, so I multiply every term by negative x over 6, plus x squared over 6 to the third. Let's write one more. Minus x to the third over 6 to the fourth, and it would go on from there. There's a geometric series with this initial first term in that common ratio. Okay, so there. Now, on our assignments and so on, we'll write our series in like a compact form. So I'll say this, and what I mean by compact form is like that with summation notation. So I could see this as 1 over 6 times negative x over 6 to the n power. And going from 0 to infinity. And this might take a little bit of trial and error for you to get. Let me make sure I've got it right. When I put 0 in for my first term, this will be a 1. I'll get 1 over 6. When I put 1 in, I'll get negative x over 6 squared. When I put 2 in, I'll get x over 6 squared, yeah. And when I put 2 in, I'll get x squared positive over 6 to the third power. Okay, so it looks like it's going to work. We could write it like that. We could write it, I would say maybe a little more simplifying. Like, what if I multiplied these together? These fractions, that's going to be negative x to the n power times 1. So I could say if I wanted to, negative x to the n power. And then down here, that's going to be 6 to the n power times 6 to the first power. So that'll be 6 to the n plus 1 power, right? Okay, so either of those are okay. They'll give you all the same numbers up there. So here's my answer. Okay. I wanted the series, all right, that is equivalent to that function. There's the summation formulas for the series. It doesn't, I don't really see it mattering which one, but I'd like you to recognize that they're both the same thing. Okay, so well, what about the interval of convergence? What are the values of x that make this thing converge, or that make this series equal to that series? Okay. Okay, so we said, well, that's a geometric series, right? R has to be between negative 1 and 1 for it to converge. So let's say, write that part down here. I need this to be true, right? For that series, this series with common ratio negative x over 6 will converge if that common ratio is between negative 1 and 1. I'll multiply this whole thing by negative 6. Whoops. When we multiply an inequality by a negative number, we reverse the, I'll get there. We reverse the direction of the inequality sign. So if I multiply this statement by negative 6, I get 6 greater than x greater than negative 6. And then I've solved for the x. It's got to be between negative 6 and 6. So we'll say the interval of convergence is negative 6 less than x less than 6. Okay. All right. So just vocabulary real quick. That thing, the numbers that cause this series to converge to that function, the numbers for which this equal sign is valid, that's called the interval of convergence. Okay? All right. So we got that problem done. Let's look at something else. Okay? All right. So think about this one. In order to do this problem, I wanted to tell you something. I want to tell you that algebraic substitutions are allowed in power series. Okay? I guess that's just by their general nature. That's the reason for that. If I could take my first problem and I say, well, look, you see this statement right here? It's true if you put something for x in between negative 1 and 1. Like, you can substitute a number between negative 1 and 1. You can put it here, you can put it here, 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 and there, and you'll get something that's true. I illustrated that by approximation here with these calculations, all right? So, you know, if now say I just give you this series, where this comes from, you know, we're not quite there yet, but let's just say I give it to you. Suppose I tell you e to the x power is the same thing as 1 plus x squared over 2 factorial plus x to the third power 3 factorial. Suppose that's true for any x. The interval of convergence for this one is negative infinity to infinity, all right? then find a power series for e to the minus 2x. Well, if I put negative 2x in place of the x's, well, I'll get it then. All right. So, all right, think of it like this. Let me, for the sake of maybe having the answer be as simple as possible, I'll say, well, it looks like e to the x is the same thing as this one. Series from 0 to infinity of x to the n over n factorial. That'd be another way to summarize that statement right there. Okay, so say I have that, all right, and that's true for negative infinity less than x less than infinity. In other words, it's true for all values of x. All I would need to do is take that statement right there and sub in place of x 2x, negative 2x. Okay, and then you'll get a statement for that one. And what's it going to say? E to the negative 2x equals series from 0 to infinity, negative 2x to the n power over n factorial. Okay? All right, it's I guess for the substitution here, it's that simple. What about the interval of convergence? Well, okay, so I guess I'd have to substitute this in there also. So that would say negative 2x is between negative infinity and infinity. But if that was the case, if by way of my substitution, then x again would be between negative infinity and infinity. All right, so there's my power series by way of substitution from a known one for e to the minus 2x. All right. In this interval of convergence, it's just a consequence of substitution into this original one. Negative infinity less than negative 2x less than infinity. If you divided all three parts of that by negative 2 in order to isolate the x, you'd end up with that. It would say infinity greater than x greater than negative infinity. Okay, which is this. So, okay, we got that one then. Got that one. Let's do this one now. Okay. So again, suppose that you're given or I give you some statement about a series being equal to a function, which is what this is right here. There's the function, there's the series. Here's the interval of convergence. Okay. Can you find a power series from that for 1 over x squared plus 1? Well, look. So again, think of the one I just told you about. Think of the premise of that algebraic substitutions are allowed in power series. All right, then for this one, I mean, I could see how you could get something for that one by way of substitution. All we need to do is sub in this original statement x squared, right? If that was an x squared instead of an x, then it would be what we're looking for, in other words. Okay, so I hope that that's obvious enough. All right. So if I do that, I'll get this. If I take this statement right here and substitute x squared in place of the x's, then it's going to say this. 1 over 1 plus x squared equals the sum from 0 to infinity of negative 1 to the n power x squared to the n power. Okay? All right, and that will be if negative 1 is less than x squared is less than 1, right? Because that's what we're using instead of x. We're going to use x squared. All right, so I've modified this statement to give me something for that one or about that function. Some simplifying. Can we do some simplifying? So yes, let's say this. 1 over 1 plus x squared equals series 0 to infinity, and let's do negative 1 to the n x to the 2n, like that. Okay? Because when we take a number and raise it to a power and then raise it to a subsequent power, we can multiply them together. So I'll just say 2n. What about this? If x squared is between negative 1 and 1, what's x between? 1 squared is 1, and negative 1 squared is also 1. I know that's kind of a really brief explanation of why you get there, but if x is between negative 1 and 1, then x squared will be between negative 1 and 1, vice versa. So I can get from here to there. So that's my interval of convergence right there. All right. Here's my statement that this function is the same or equivalent to that series, but only for those values of x, right? Not for just anything. It's got to be those values of x right there. Okay, yeah, and what do I mean by that again? Well, it's like try to keep your mind on task here. I just mean that, you know, if you start putting numbers in the function and numbers in the series, you'll get the same thing if the series were infinite. If the series was truncated, then you'll get some degree of approximation. All right, that's what I'm saying about all of these. About this one, yeah. If you don't believe me, take an x in there, put it in this function, put it in this series, run that series out as far as you want to, add it all together, and you'll see that these are very close to each other. Okay. All right. Let's see, what else do we got? Okay. Well, so beyond that, let's take. I'm afraid a theorem is unavoidable at this point. I told you there'd be some fine print and some details to this. And I think here that gets ramped up a little bit. So let's say that I give you this statement. And I say, well, there's a function and it's equal to a series. Okay? So at this point, we've seen examples of that. A function being equal to a series. All right. And let's say, well, they're the same for some interval of convergence, whatever that is. Okay? All right, so it could be like the interval of convergence is negative k to k, or it could include the endpoints too. I told you there was lots of fine print. But let's just say that it has some interval of convergence. All right? Okay. Then you can modify this statement in terms of differentiation or integration. Okay? All right. So if f of x is equivalent to this series, then f prime is equivalent to this one. What's this look like? What's the derivative of a naught, which is a constant, plus a1x plus a2x squared plus a3x to the third? Well, you're going to get a1 plus 2a2x plus 3a3x squared. All this series is the term by term derivative of that one. Okay, so if a function is equal to a series, that function's derivative is equal to the term by term derivative of that series there. All right, so establish that. What about antiderivatives or integration? Well, okay, so the antiderivative of this function would be equal to, what's this look like? A naught x, a1 x squared over 2. Term by term, these are the antiderivatives of that series, okay? Plus some constant of integration. You know, if I was going to take find the antiderivative of all these terms right here, which is all that represents, there would be a constant of integration. All right, so that's got to be there. But there's your statement. Okay? Now, so but without getting into the fine print, if a series is equal to a function, then you can operate on that statement by differentiation or integration. Okay? Now, some fine print, though. Unavoidable fine print. The new series you get, okay, right here, that will have the same radius of convergence. It won't necessarily have the same interval of convergence. So that means that, I don't know, like say, example, -1 to 1. Say that's the interval of convergence. The radius of convergence is 1 on that interval. And say I have this by contrast, -1 to 1 with brackets. Here I'm including the endpoints. the radius of convergence is still 1. All right? So when we get this new series over here through the operations, then it has the same radius of convergence. That doesn't mean that the interval is exactly the same, because this interval and that interval have the same radius. That just means that we have to check the endpoints of the interval of convergence when we do this, okay? All right, so I've said that. I've gone through the fine print. So let's look at an example of that. So here, this one, I give you an initial statement, and I want you to do something to it to find the power series for some other function. So my statement here says that this function is equivalent to that series for all x's between -1 and 1. All right? So can you find a power series for this function? Okay. Now what I notice about these, just looking at them, is if I took the derivative of this, I would get 1 over 1 plus x. So if I found the antiderivative, the indefinite integral of 1 over 1 plus x, that would be natural log x plus 1. Okay. So here's what I can get then. The series for this function would be the term-by-term integral, or term-by-term antiderivative of that series, okay? So here's what we'll get. We'll get natural log x plus 1 is equivalent to this series. There will be some constant of integration plus, what's the antiderivative of 1? It's x minus x squared over 2 plus x to the 3rd power over 3, okay, minus x to the 4th power over 4, and then that keeps going. All right, so the antiderivative of this is equal to the antiderivative of that plus some constant of integration. Okay. Now, before I work on this anymore, I need to know that constant of integration right there. Okay, so how do we figure out what that number is? We'll solve for c. And we can do that by choosing a convenient value of x, in there. Like, so suppose I let x be 0. And it says natural log of 1 is equal to c, and then that's 0 minus 0 squared over 2 plus 0. Okay, and what's natural log of 1? It's 0, so therefore c is equal to 0. Okay, so yes, there is a constant of integration there, but it turns out to be 0. All right, so let's take this a little bit further. I'm now reduce my statement to this. Natural log x plus 1 is, because we found that constant of integration to be 0, it's going to be x minus x squared over 2 plus x 3rd power over 3 minus x 4th power over 4 plus, and it keeps going. Where all these are the individual antiderivatives of what I started with, okay? All right, so now suppose we get there. Suppose we can get to that point. Let me write an answer, but put it in summation notation. Okay? All right, so I think if we do like this, now I told you this part will have some trial and error, so if I get this wrong the first time, I'll check it and I'll fix it. But it'll be, so let's see, 0 to infinity, and the series is alternating. So let's do like this. Okay, so I think that'll do it, but let's check it. So I put 0 in, that -1 to 0 power is 1, and that's going to be x over 1, so that's x. Then I go to 1, I'll get, it's negative x squared over 2. Okay, so that's going to work. So there's my statement. This function is equivalent to that series. Now, all right, now what did our theorem say that we were talking about? It says that this will have the same radius of convergence that that does. Okay? So here the radius of convergence is 1. And so that means that this has the same radius of convergence. So that means that at the very least, that's the interval of convergence. Okay? But I said it's got the same radius of convergence. Okay? It doesn't mean the interval is the same, and this means we have to check the endpoints whenever we develop things like this. Okay? All right, so we got to check those endpoints. So here goes. In order to check the endpoints there, that means on a case-by-case basis, I have to see, does this series converge if x is 1? Maybe it does. Okay, so when I let x be 1, I get negative 1 to the n, and when I put 1 in there for x, well, what's that going to be? Well, 1 to some power is just going to be 1. So it's going to be 1 over n plus 1. Okay? And this is an alternating series that converges. An alternating series converges if its terms get consecutively smaller and if its terms go to 0, which happens in this series. How you tell if an alternating series converges or not, that's in a different video and a different lesson, all right? So, okay, I got to include the 1, okay? All right, what about the negative 1? All right, so x is equal to negative 1. That will give me this series from 0 to infinity, negative 1 to the n power, and I put negative 1 in there for x. Negative 1 to the n plus 1 over n plus 1, right? Does that converge or not? Well, let's do a little bit of combining and simplifying in order to figure that out. I noticed that these are like terms, and I can therefore multiply them together. So let's say like negative 1 to n plus 1, right? That's what you're going to get if you add those exponents over n plus 1, okay? And this is always going to be an odd power right there. So if you want to see that, I mean, an even number is a multiple of 2, an odd number is a multiple of 2 plus 1. But if you put 0 in, it's 1. If you put 1 in, it's 3. If you put 2 in, it's 5. That's always going to be odd. And if that power is always odd, that means that, well, that's just negative 1. Okay? And this series diverges. Okay, so we don't include negative 1 in the interval of convergence. It's just that we include the 1. All right. Now, so one more thing. And there's always one more thing when you get to this point in calculus 2. How do I know that series diverges? Well, because it's just a portion of, it's really just like this p series. Okay? So let's take this p series, 1 over n, and that's 1 plus a half plus a third, okay? And it keeps going. That p series diverges. This p series is also called the harmonic series. It diverges. What's this? Well, so this is negative 1, negative 1/2, negative 1/3, if you write it out. It's all this, but the numbers are negative. It's not going to converge either. If this one doesn't converge, neither is that one. Okay. All right, so we got this one. Is the radius of convergence here the same as in that initial statement that we worked with? Yes, same radius of convergence, different interval of convergence. All right. Okay, I told you there'd be some fine print. Don't say I didn't warn you. Let's try another one. Okay, so here goes. I wanted to do a problem, I don't know, based on one that we just did. I thought I might do some that are consecutive with each other. All right. So take this one. And let me get that other problem back. All right. Oh, okay, so here it is. So I wrote down the same thing. Okay. All right. So here it says this. Can you use that statement right there, that this series and that function are the same, to calculate the grand total of this series that converges? And what I notice is this series is not a geometric series. Okay. Now, anyway, all right, so it isn't. But it looks pretty close to the way that one is. It doesn't look identical, but it looks similar. Okay? So here's what I thought we would do. Let's see if we can work this around so that it looks more like that one. And then if I can show that these are the same somehow, then I can use this function to calculate that. It's kind of like how I started off and I said, well, this function equals to that series. So you can go about putting numbers in. And the function and the series will agree with each other. All right, within a certain margin of error. All right. So I'll try to do that. So let's do this. I'll take this and I'll rewrite this and then I'll manipulate it so that I can use it. So here's what I started with. Okay, and I want it to look more like -1 to the n plus 1 power over a number to the n power times n. Okay, so I guess the first thing I might do is in order to get that to be n and not n plus 1, maybe I'll see if I can do this. Do you see how we have some freedom in how we express that initial number down there? Like if I was going to put a 1 in, then all I'd have, if that was going to be my first number, if that was where I was going to start, then all I would have to do is adjust these things over here, right? So think about it like this. If I put 0 in first for n, that power right there is initially 0. And if I want to change it to be 1, then that means this now has to be n minus 1. So that ultimately that number we get is still a 0 right there. You see how the calculation is equivalent? Put 0 in. -1 to the 0. That's your number. Put 1 in. -1 to the 0 again. And how's that going to change this? This will be n, and this will be n. Okay. So we can start there, and that looks a little bit more like what I'm trying to work with. But it's not perfect, all right? Because, well, why isn't it perfect? Well, it starts at 1. Okay, so it's got that. It's got n. And -1 to the n plus 1, though. That's n minus 1. But are they any different? Isn't this the same? Since that's just a -1 right there. Wouldn't it be the same as this? Try it out. That right there, okay, gives me -1 to the 0 power, which is 1. Then when I go to 2, it gives me -1 to the first power, which is -1. This is just going to alternate right there. That's all it's going to do. It's going to be a 1 and then a -1, and a 1 and then a -1. Same thing here. When you put 0 in, it's going to be a 1, then a -1, then a 1, then a -1. So I could change it like this, get that. These are now going to match what those would give me. And now this, like, what's this going to do? What's the first number you're going to get right here? -1 to the second. That's 1. And then how's it going to go from there? It's going to be a 1 and then a -1. That's why these are the same thing, okay? Maybe that would surprise you, but if you did all the math and you wrote it out, they would be the same thing, okay? All right, so now ultimately, here's what I'm getting. I just to change things around in appearance, I can say natural log 1 plus x is all this, okay? That does look like this. You might say, well, it looks like that 7's out of place. Okay, what if you took this statement and put in for x 1 over 7? it would be that. That's what it would be. It'd be the series from 1 to infinity of -1 to the n plus 1 power of 1 over 7 to the n power over n. That's the same thing as just putting the 7 down there. All right? So, okay. It's just a matter of algebra, but yes, this is like saying 1 over 7 to the n power over n. Okay? And that's what this would look like if you put 1 over... So we got it. Then, if I put 1 over 7 for x right there, that's this series that I was initially trying to calculate. That's going to be equal to natural log of 1 plus 1 over 7. Okay? All right. So that thing right there, I was trying to calculate. This series, its grand total, is going to be natural log 1 plus 1 over 7. Okay? I'm going to pause the video because I want to write that statement down. And there it is. Okay? You want to know what this is? That's it. Okay. Now what is that then? Natural log 1 plus 1 over 7 is an irrational number that's going to take some rounding. So let's see, calculator. Calculate it to so many decimal places. You'll get 0.1335. It's about 0.1335. Okay. So that's what this is. If you wrote that series out and you start doing all the math, that's about what you'd get with some rounding. Okay. So, all right, that's how that one works. Let's look at a few more. What about this one? Okay. I wanted another example, sort of like the one I showed you before the last one. Okay. And what I mean by that is I give you an initial statement that a series is equivalent to a function for an interval of convergence. Can you give me a power series for some other function? Okay. And I guess like we'll just have to, whenever we do this, we'll have to see what we notice about what we want and what we have. All right. And I look at this and I notice, is there any way you can get this from that somehow? Is there something that you would do? And I'll note to you that the derivative with respect to x of negative natural log 1 minus x is going to be 1 over 1 minus x. Okay, so you could, if you wanted to make this modification, we could integrate this whole thing, right? Yeah, because what's the antiderivative of 1 over 1 minus x? It would be negative natural log of 1 minus x. So that's what we want. Okay, so say I do that. The term by term antiderivative over here is equal to the antiderivative of that. Then I'll get this statement. Negative natural log 1 minus x is equal to, well, there's got to be a constant of integration. We talked about that when I told you about the fine print for some of this stuff. Remember that we can take some initial statement about a series being equal to a function. We can find the antiderivative of both sides of that, but there will be a constant of integration. So some constant of integration. What about over here? What's the antiderivative of 1? It's x, and of x, that's going to be x squared over 2. And of x to the third power, that's going to be x to the third power over 3. And that will go on like so. Okay? What's the constant of integration? Well, in the last problem, it was somewhat similar to this one. It wasn't identical. But we got to this point. I said, well, there's going to be this constant of integration. We put in a value of x into our statement. 0 is a nice convenient number. And we solved for c, and it turned out to be 0. Now, this one will work a lot like that. When we do that same kind of thing here, we'll get 0 for c. Okay? And you might say, why do you bother to tell us that if it just turns out to be 0? Well, it is there, and who knows? You might find out that it's not 0. But you put in a convenient value of x, and then you solve for c, and that way you know what it is. All right, so let's take a little further. Negative natural log 1 minus x is, given that that constant of integration turned out to be 0, x plus x squared over 2 plus x to the third power over 3, and on and on. Okay, so, well, all right, is there some brief simplified form to write this? That part, like the series, is there some simpler way to say it? Looks fairly easy that I could do like this. Let's do n is 0 to infinity, x to the n plus 1 over n plus 1. That'll do it, right? But let's go ahead and check it. If you put 0 in, you'll get x to the first power over 1. If you put 1 in, you'll get x to the second power over 2, and on and on. So I got my statement. I found a power series for that function, negative natural log 1 minus x. But it only converges, that series only converges to this function for certain values of x. You can't put anything in for x. It's just certain things, certain x's. All right, and that's called the interval of convergence. Well, when we talked about our theorem, it said that the radius of convergence is going to be the same. So that means that the interval for convergence here is going to be -1 less than x less than 1, with the possibility that this series might converge at the endpoints. It might converge at 1, it might converge at -1. So we'll remember that we have to check the endpoints. Okay. All right, so first endpoint, let's try 1. All right. Does this series converge when the x is equal to 1? When the x is equal to 1, that's going to be 1 to the power n plus 1. It's always going to be 1. So it's going to be 1 over n plus 1. So that diverges. And we saw something similar to that earlier, but it's basically this p series. That's a p series that diverges, so this one does also. And what about -1? Okay, so if I let the x be -1 right there, I'll get -1 to the n plus 1. All right, over n plus 1. And that's an alternating series that converges. Okay, it's an alternating series. It's going to go from plus to minus to plus to minus and so on. Or actually, this case, it will go minus to plus, minus to plus. The terms get consecutively smaller, and the terms go to 0. So it converges because it's an alternating series that converges. I'm not saying here that every single alternating series converges, just that this one does because it passes the alternating series test. So, all right, I've got to update my interval like that. The interval of convergence is -1 to 1, including the -1. All right, so let's do one more on that theme, and then one final example after that. Let's see, yeah, okay. So it says use the power series representation for this function to get the power series representation for that one. Okay? All right, so maybe somehow by knowing something about this function, you can figure out something about that one. So in other words, let me look at it like this. I have this. And I want some series that works for this one. Okay? Now, to start with this, since that's what I have, this does look a little bit familiar. That's the kind of formula that I get from a geometric series. So in other words, a geometric series could converge to that, all right? because it looks like a1 over 1 minus r. So in fact, a geometric series with first term 4 and r equal to x would converge to this. All right? So that means it comes from the series 4 plus 4x plus 4x squared plus 4x the third part. You get the idea. All right? Okay. And is there some interval of convergence for that? Yes, it's 4, -1 less than x less than 1 because r is x. All right? So that's at least a starting point. You know, I have to, it says use the power series for this to get the power series for that. Well, at least now I've got the power series for 4 over 1 minus x. I just recognized that it's a geometric series, okay? All right, now, is there any connection between the two of these? Is there something that you do to this one to get that one? All right, so think about that for a second, and I'll remind you of something that we talked about. Let me see. How can you manipulate these statements? All right, say you have a statement that some function is equal to some power series. You could differentiate or integrate to get another statement. Okay? All right, so let's say I have this, and then I notice something. The derivative with respect to x of 4 over 1 minus x is 4 over 1 minus x squared. All right, it's true. True statement. If you take the derivative of this, you get that. All right, now, so that means that if I differentiated this statement, on the left-hand side, it would say 4 over 1 minus x squared is equal to, on the right-hand side, whatever the derivatives of all those are. All right, okay. All right, so say we do that, then we'll get 4 over 1 minus x squared, which is the derivative of this, equals to, what's the derivative of 4? 0. What's the derivative of 4x? 4. So the derivative of 4x squared, 8x. 4x to the third, 12x squared, and then it keeps going. Okay? All right, all right. So let's do this from here, though. I got my statement, and that right there, that statement, that could serve as an answer. If you want to know what's the power series representation of 4 over 1 minus x squared, there it is. But I want to, like I've been doing in the others, I want to write like compact notation with series notation, okay? So in order to do that, I mean, I guess I could try to figure something out right there as far as what this is. That's one way to do it. Another way to do it is, you know, I can think about this right here, okay? What does this look like? Okay, see that? The terms of this series look like 4 times x to the n power, n going from 0 to infinity. That's what they look like. What would you get if you took the derivative of that? 4n x n minus 1. Okay, so let's try that here. 4n x n minus 1. Okay, where would we have to start our counting though? 1. 1 goes in. We get 4 times 1, x to the 0 power. That's 4. 2 goes in. You get 8, x to the first power. 3 goes in. You get 12x squared. Okay, it's going to work. That's it. N goes from 1 to infinity. All right. What's the interval of convergence? Well, the radius of convergence is the same as that one. Okay. Like that. All right. What about the endpoints? It's got the same, this has the same radius of convergence as that, but maybe not the same interval of convergence. So I've got to check the endpoints of that. All right, that's just how it goes. I think this time it will be easy to check the endpoints. If x was -1, my series here would be 1 to infinity 4n -1 to the n minus 1 power. Which that's going to be a series, it's going to be alternating, it's going to be 4 and then 8 and then 12. And a series like that, it's not going to converge. All right. You can write it out if you want to, but it's not going to converge. All right, what about 1? That's just going to be the series from 1 to infinity for n. Because if that x is a 1, it's 1 to various powers, which is always going to be 1. Well, what's that look like? 4, 8, 12, 6. If you add all that together, it's not going to converge. Both of these diverge, so we don't need to update that interval right there. Okay? All right, so let's do one more based kind of off this one, okay? Not totally, but a little bit. And there it is. Okay, so if, again, I give you a statement to work with, can you calculate something from it? All right? So I give you this statement that 1 over 1 minus x squared is equal to the sum from 1 to infinity n times x to the n minus 1. Okay? Can you use that somehow to calculate this? All right. Now, I noticed, like has been the case for other problems that we've looked at, that if I'm supposed to use this to calculate this, there is some similarity between the two of them. They're not identical, but they're similar. All right, they look something kind of like each other. The difference with this one and how it doesn't really look exactly like that is that power is n and that power is n minus 1. Okay? All right, so let's work on that. We'll reconcile that somehow. So I could do this. So I'll write it down. And then I'll talk a little bit about my rationale for it. See that? See that right there? Okay, why is that true? Well, so it's like I factored this out of that. Is it true that when you multiply like things, you add the exponents? That's true. What's the exponent here? It's 1. So what if I multiply them together? What would I get? 10 over 11 to the first power, right? Plus n minus 1. 1 plus n minus 1. That's just n. Okay? Now, that is just a constant. And constants can be factored out of summation because they are constant. They're the same in every single term. It's like that 10 over 11 is going to be a common factor in this series if you write the whole thing out. So I'll get, if I factor that out with this number that's already there, I'll get 10 over 11 squared times the series from 1 to infinity n times 10 over 11, say the n minus 1 power. Okay? Now this does look just like that, except for the x is 10 over 11. All right? So I can, at least this right here is going to be what? How can you calculate this thing? You can calculate it by that function. So at least this part right here has x being 10 over 11 and is therefore going to be 1 over 1 minus 10 over 11 squared. Okay? All right. So here goes my final calculation for this. It's going to be 10 over 11 squared times 1 over, what is 1? Let's do this part. What's 1 minus 10 over 11? It's going to be 11 over 11 minus 10 over 11. That's going to be 1 over 11 squared. Okay? And that looks like 10 over 11 squared times 11 squared. So it's just 10. All right. So yeah, if you do this series, do all the calculations out to infinity, you're just going to get 10. It converges to 10, in other words.